In our lesson today, we are practicing the heats of formation, checking our homework page. We understand that the delta H of formation, creating a compound from its constituent elements, really is an application of Hess's law. We are remembering that delta H for a reaction can be found by simply taking the sum of all of the delta H of products minus reactants. There, I have it written correctly for us. Products minus reactants. The tool page we use to apply Hess's law is our thermodynamic quantity. I've photocopied for you. It's in Appendix C. The heats of formation are in the first column of our appendix, and they are listed alphabetically, starting with aluminum, and we can see that the elements will go through alphabetically all the way down through the element zinc on the opposite side. Let's begin with our first question. Using our Appendix C, calculate the standard enthalpy change for the following reactions. We have gaseous sulfur dioxide combining with molecular oxygen, forming sulfur trioxide, and the states of matter are provided so that we correctly use Appendix C to find the heats of formation. And that's what you see I've done ahead of time. I'm using my Appendix C. I found the SO2 in the gaseous form under sulfur. Sulfur dioxide in the gaseous form, I recorded at negative 296.9. While I was there, one beneath that, sulfur trioxide, negative 395.2. And of course, we've learned that any element found in its natural state, such as oxygen as a diatomic molecule, has a value assigned as 0. The way that we find elements in nature do not take energy to create. They are the building blocks with which everything else is created, so of course their value is 0. So here we begin with just a practice of looking at each individual value found from Appendix C and applying the heats of reaction can be found by taking the products minus reactants. So in our first equation, the product value, we have 2 units of SO3, so 2 distributed through the value of negative 395.2 is the sum of all of the products minus. We have 2 units of SO2, each at a value of 296.9, plus the value of molecular oxygen, which would be 0. The sum of the products minus reactants. Let's hit together and see if we get a common answer. 2 times the value of negative 395.2 minus 2 times the value of negative 296.9 plus 0. And the overall reaction looks like it's exothermic, negative 190.6 kilojoules of heat. Negative 190.6, the sum of products minus reactants. Letter B is very similar. I took the time to find, using Appendix C, the individual components of our equation. Magnesium hydroxide, found under the magnesium element, MgOH taken twice as a solid, found right here in our Appendix C. And while I was in magnesium, I tried to find all the like elements at the same time. Magnesium oxide was found as well, negative 601.8. The other guy here, water, in the liquid form, you might be tempted to look for water under the H's. It's just odd. The water, you'll see, is under oxygen. So water in the liquid form, different than water in the gaseous form, so be careful you're finding for liquid and not steam. Liquid value of negative 285.83. And so that's why I had recorded that information earlier. The delta H of our reaction is found by taking the sum of the products minus reactants. So we have the MgO, negative 601.8, plus the value of liquid water, negative 285.83, is the sum of our products minus the reactant, which is negative 924.7 kilojoules. Let our calculator do the work. Negative 601.8 plus a negative 285.83 minus negative 924.7 equals, here we have an endothermic process with a value of positive 37.07. Positive 37.07 kilojoules of energy. Heat absorbing. Same process for letter C. One at a time, I had taken the value to find each of these under the Appendix C, remembering that water here is in the gaseous form, so a little bit different than up above in the liquid form. I found iron chloride, hydrogen chloride, and iron oxide. Remember that hydrogen chloride would be found under chlorine. Remember that the last name for hydrogen dictates where it will be on the alphabet for whatever reason. That's how they've organized Appendix C. But I found iron compounds in this area, and then of course HCl under the chlorine. So I've done that work for us. Let's go to work and check our answer. The delta H of reaction is equal to the sum of the products minus reactants. Here I have 3 units of water, each at negative 241.82, plus 2 units of the iron chloride, each at a negative 400, minus the sum of the reactants. The iron oxide is at a value of negative 822.16, and there's just one of those, plus 6 times the value of 92.30 gives me the sum of the reactants. Let's let the calculator do the work. Delta H of reaction is found by taking 3 times the value of negative 241.82 plus 2 times the value negative 400, and we get the sum of our, I'm just kind of simplifying this side first, the sum of the products. Then I'll take that answer minus, and I'll use double parentheses here, negative H22.16 plus 6 times negative 92.3, close those parentheses, and then missed a decimal, 92.3, and I get a value of negative 149.56. So this is an exothermic equation, negative 149.56 kJs. And one more on this side, and again I've taken the time already, looked up Appendix C values. The delta H of reaction is equal to the sum of the products minus reactants. Here we have potassium carbonate. And potassium on the back side of your Appendix C, so here's the list of where I found the potassiums. We had 1 unit of K2CO3 that was found to be 1150.18. 1 unit of gaseous water, negative 241.82. There's the sum of my products, minus, I have 2 units of KOH, plus 1 unit of the carbon dioxide. Hit with me, make sure we get a common answer. Negative 1150.18 plus negative 241.82 is the sum of my products. Then I'll just hit minus, and I'll use double parentheses here. 2 times negative 241.7 plus negative 393.5. And when I hit enter, did you get the same thing I did? Negative 515.1 kilojoules. An exothermic process, heat releasing. So with our front value, we simply took the time to look up each one of the values from our Appendix C, summed the products, subtracted from the sum of reactants, and came up with a value for the delta H of reaction. On the back side, we had a little different format. Given a thermochemical equation for the combustion of acetone, which is nail polish remover, C3H6O as a liquid, combusts, so we understand that reacts with molecular oxygen, forming gaseous carbon dioxide and liquid water. Heat is released. See the negative sign for exothermic, negative 1790 kilojoules. Using this information and the data from our Appendix C, calculate the enthalpy of formation of acetone. So this becomes our target variable. We'd like to know the heat of formation for the reactant. So we know the sum of the reactants minus, I keep saying that backward, products minus reactants is equal to negative 1790 kilojoules. If I take a quick moment and look up the values of everything else we know, the elemental form of oxygen we understand to be 0. Any element in its natural state is assigned a 0. Carbon dioxide in the gaseous form, CO2 as a gas, is negative 393.5. And water, remember it's under oxygen, in the liquid form, water as a liquid, negative 285.83. So I've used Appendix C to determine those values. Here's what we're being asked. The sum of the products minus reactants. We have 3 units of carbon dioxide plus 3 units of liquid water is the sum of the product minus the sum of the reactants, which is X plus 0, or I'll simply write that as X. This is what we're trying to solve for, the heat of formation of the reactant. So we're letting X stand for delta H of formation of C3H6O. Well, let's simplify what we have inside this parenthesis. 3 times negative 393.5 plus 3 times negative 285.83 gives me a value inside of this parenthesis as negative 2037.99. Multiplying through and adding, I simplified inside of that bracket. So we now have negative 1790 kilojoules is equal to negative 2037.99 minus X. Let's add 2037.99 to both sides, and we'll get what's equivalent to minus X. Negative 1790 plus 2037.99, and that's 247.99. So what is X equal to? If I divide out both sides by negative 1, X came out to be 247.99 kilojoules of heat. So the heat of formation of our acetone, 247.99 as an exothermic value. And one more will complete our homework set. Propanol, C3H7OH, is often sold as rubbing alcohol. Isopropyl alcohol is another name for it. Perhaps you have it in your medicine cabinet at home. The complete combustion of this substance yields, liberates, releases. It's all telling us that it's exothermic, giving off heat at 847 kilojoules for every 1 mole. What would the balanced equation for the formation of propanol from its elements? We want to make propanol, C3 H7OH. Well, what are the elements that produce? We'd have the elemental form of carbon, C. The elemental form of hydrogen is diatomic, H2. And the elemental form of oxygen, O2. Let's balance. Right off the bat, I'm noticing that I have 2 H's, 8 H's. Oops, I got an odd number of oxygen, so I think I'm going to need to double there to get the O's to balance first, giving me 6 carbons. There's 8 times 2, so I'll have 8 hydrogens, and of course 1 oxygen. If we wanted to, and this is, I know, is new, but if we wanted to keep this in terms of per mole, we could have written, and it's okay, we could have written a 3 to 4 to 1/2, creating a single mole of propanol. And that way, the delta H would have remained 845 kilojoules per mole. And it would be negative, it's exothermic. If, like me, you made 2 moles of it to balance an equation without a fraction, we made 2 moles. So now when I doubled it, the delta H would become 1690. So this equation, the way I have it written, would be kilojoules for 2 moles, or in the above equation, kilojoule per mole. Alrighty. Write the balanced thermochemical equation for the complete combustion of propanol. So now I'm going to take that product, C3H7OH, we're going to combust it. And a complete combustion produces carbon dioxide and water. And let's balance first. Let's see, 3 carbons, I have a hunch I'm going to do this in pencil. 3 carbons, 8 H's, and that gives me 6 and 10 oxygens. Minus 1 is 9, so therefore I know that I need a fraction there. So I'm going to go back, and that's why I had kind of suspected. Now I'm ready for pen. I think I'll do a 2, 6, and now just know here there's 8 hydrogens. Alrighty. And now we can count oxygens. 6 times 2 is 12, plus 8 is 20, minus the 2 that I have here. I need 18 more. There we go. But because I placed a 2 to balance this equation, I'm going to make sure I keep the 1690 kilojoules. 2 to 9 to 6 to 8, that 2, because it said per mole, I just simply doubled it. Alrighty, keep that proportion the same. Let's calculate the enthalpy of formation of propanol. So in other words, I'd like to know the heat of formation of propanol, which really is this particular equation. I know molecular form of oxygen would be 0. CO2, I looked up earlier right here, negative 393.5. And water, and again we'll put this as the liquid form, negative 285.83. So here's what we know. Negative 1690 kilojoules is the heat of formation for the reaction. Alrighty, delta H of reaction. It's equal to the sum of the products. I place 6 units of carbon dioxide, each at negative 393.5, plus I have 8 units of liquid water, each at a value of negative 285.83. There's the sum of my product minus the sum of my reactant. Keep in mind there's a coefficient here, so now I have 2x plus 0. Let's simplify the interior bracket here. 6 times negative 393.5 plus 8 times whoops, I hit a wrong button, negative 285.83. And this I'm finding is negative 3467.14. So negative 1690 is equal to negative 3467.14 minus 2x. Let's bring this guy to this side. So I have negative 1690 plus 3467.14. Alrighty. So far here I have 1777.14 is equal to negative 2x. Let's divide both sides by negative 2, get the x by itself. So I have that on my screen. I'll divide by negative 2 and negative 888.57. And that's an exothermic quantity, the heat of formation of our isopropyl alcohol. So just to recap very quickly, we had 4 practice problems in which we just simply summed products minus reactants and found the delta H of reaction. On the back side, we worked a little different strategy. We knew the delta H of reaction, and it actually was the reactant that became our target variable. In the first question, we were targeting the acetone, that became our X, and down here we were targeting the alcohol. Because I had a coefficient with it, I made it 2x and just divided that simply out. Alrighty. You're now ready to turn your homework page in and proceed to the next part of your lesson.